Hello, this is Dr. Chunendra Sahu from IIT Kanpur, and I am going to teach environmental fluid mechanics in this semester. So today is the first lecture of this course titled Environmental Fluid Mechanics, which we will be doing over the next 8 weeks, and it will have about 20 hours of lectures. So in this course, we will start with the basics. We'll first understand what exactly environmental fluid mechanics is, how it compares with other uh, uh, disciplines of fluid mechanics, what is its importance, and then we will go into quickly revise some concepts of fluid mechanics, for instance, governing laws, and then we will study different processes that we uh, have in this course one by one. Okay, and that we will be covering in next over 8 weeks. So, environmental fluid mechanics, as the name suggests, this is the study of the fluid mechanics in the environment. But if you want to see an exact definition, then we can define it as EFM is the scientific scientific study of naturally occurring flows of air or water in the environment under the ambient temperature and pressure conditions. Okay, so this is how we can define environmental fluid mechanics, where we try to study fluid mechanics involving air or water in the environment in the ambient temperature and pressure. So few things that we need to note here is first air or water, right? Then the second point is naturally occurring flows. And then the third point of interest is at the ambient temperature and pressure conditions. So why do we focus only on air or water? So that is because these are the abundant fluid which we encounter most of the time, and environment usually is either air or water. And then within air or water, we may have different components of other gases or fluids, but they mostly work as contaminants, not really as the ambient fluid. So air and water work as ambient fluid most of the time, where we have some other gases or liquids working as contaminant fluid in the system. And that is why in the environment we mostly encounter these two fluids. But now if you think about some engineering applications, right, they're not necessarily fluid is always air or water. For instance, uh, petroleum pipelines, the fluid that is there is actually petrol, diesel, or some other fluids, right? Something related to petroleum, but not really air or water. And that's why those fluids are more of engineering type fluids. Here we are focusing mostly on air and water medium with contaminants of other gases and liquids. And the next point is naturally occurring flows in what it means. So here we are not really looking into the forced flows or flows that is driven by a particular system, but we are looking into an open medium where the flow is happening either because of temperature difference or pressure difference or density difference, etc. right? So if you look at this condition, these two images, which are an example of naturally occurring flows. So in the left example, we are seeing circulation of hot and cold air near the seashore in the coastal regions at the daytime and nighttime. So if you look here at the daytime, this air is generally warmer, that is coming from the land side, and that's coming from the sea side is cooler. Why? Because land gets heated up much more quickly compared to the water body, right? So during daytime, the hot air actually flows to the right at the upper layer, and the cold air flows to the left at the lower layer, right? And that is how circulation happens. And now, when you think about the same system at night, which is here, now the land gets cooled much more quickly than the water body, and that's why now we have cold air which is coming from the land and flowing towards the ocean at the bottom layer, and hot air from the ocean, comparatively hot air, that is coming this way. And why hot air or warm air is always above the cold air? Because there is density difference. There is hydrostatic pressure. So at the bottom, when the density is more, the pressure is more, and because of that, the ambient fluid or warmer fluid which has lighter density, that tries to rise up because of the buoyancy, right? And that is how circulation happens. Similarly, if you look at this other example, which is of the plume, right? So this is smoke stack from which this hot gas is coming out, right? And what you see here in the ambient is the ambient air, right? So this one is ambient air at atmospheric temperature and pressure. Now, because hot air is coming out of this smokestack, it is lighter in density, right? And because it's lighter in density, it has buoyancy. It has buoyancy force, and that tries to rise the fluid upward. So these flows that you see here are the naturally driven flows. Now you may argue that there might be a pump attached here, somewhere here, pump or fan. But once the hot gases come out of the smokestack, that flow is a naturally driven flow, because that what you see here is happening because of the buoyancy. Right, so when we talk about environmental fluid mechanics, we focus on fluid flow that is happening because of the density difference. And that density difference may be because of the temperature difference or concentration difference. So these are few things we are focusing here. Okay. Another thing that we have uh, here is ambient temperature and pressure conditions. So while the plume itself, in this case, for instance, here, this might have higher temperature, but the ambient that you see, that is at atmospheric temperature. That does not have higher temperature than the atmospheric temperature, right? So when we say ambient temperature and pressure, we are mostly referring to the atmospheric temperature and pressure, and only the fluid that is coming out or that is mixing with the air or water, that might have different temperature and pressure, and that in fact brings the buoyancy, right? Which is important for these naturally occurring flows. So this is a simple definition of environmental fluid mechanics, right, that we are going to study in this course. So now let's look into the importance of environmental fluid mechanics. Why studying this particular topic is important in first place. So if you look into these two examples that we have at the top, right? We all know that we are all immersed in fluids. We are immersed in fluids, right? It can be air when we are, so we are basically immersed in air, and from air we get our oxygen, right? Whereas aquatic life like fish or other oceanic life, they are immersed in water. In for both our survival, either we are in the atmosphere here or in the water, for example, for fish, we all survive on the motion of these fluids. It can be air or water, right? So if you think about this breathing in and breathing out system of our own, what we do is we breathe in and we breathe out, and when we breathe out it's CO2, right? And once we breathe out, that CO2 is just outside your nose, but now because of this naturally driven flow which is happening all the time, that CO2 actually gets dispersed in the nearby atmosphere, right? And now in the next moment when we breathe in, we are not actually breathing in the same thing that we uh, just breathe out, right? So what we are breathing in is different from what we are breathing out, and that is happening because there is a naturally driven flow at all time, right? And that is happening because there is sudden temperature difference or pressure difference, or there is this concentration difference, right? So this difference in temperature, pressure, or concentration is driving that naturally driven flow, right? So for our survival, for this human life, or this whole ecosystem in the earth, this naturally driven flow is important. Because of that only we are surviving, or our life is possible that way, right? Likewise, in case of aquatic life, there is this oceanic circulation, right, that happens both at the earth scale as well as at local scale, and that actually circulates the water, and also that kind of maintains the oxygen level and many other components depth wise throughout the year, constant, or depending on the time of the year. So there is continuous circulation of different uh, of the water, and that maintains your uh, the percentage of different gases that is needed in the sea, in the oceanic water, right? So that is the first importance of these naturally driven flows, and why we study it, right? The whole life is actually dependent on the naturally driven flows, right? Now the second example is coming from these two images, right, where we see there is uh, pollution that is coming because of, for instance, this stubble burning. We all have seen in recent past that in cities like Delhi, New Delhi, it gets highly polluted during the winter days. That happens for several reasons, and one of the reasons is this stubble burning in nearby regions. So that stubble burning creates a lot of these polluted gases, and that actually flows towards the city and it gets trapped there, right? And especially it happens during the winter, and there is another reason why it happens more during the winter, not in other seasons. So that is another thing we are going to see. But what actually happens here is, when there is this hot gas that is getting created at one place, but it is transporting from that place to another place, right? So that transport that is happening, that is again happening naturally. We are not really using a fan or pump or anything to transport that hot gas from one location to another location. That is happening naturally, but at the same time now we want to predict how much of that hot gas is going from one part to other. We need to study it physically, right, using some physical concepts, and that is where environmental fluid mechanics comes into picture. We try to see how much of this, with what velocity this hot gas will flow, with what concentration. If we look from 100 kilometer from here, what will be its concentration? Is it same as concentrated as it is here, or it will have got diluted, right? Likewise in this case, in example one, where we have this hot gas coming out, so it is rising up because of buoyancy, right? And because it's rising up, there is mixing happening from atmospheric air into the hot gas. So because of mixing, now it has to get diluted. So it gets diluted and slowly its concentration decreases, right? But now if you want to predict at certain distance away from this smokestack, we would have to apply some physical concepts, right? And that is something we are going to see again in this course. So that is where environmental fluid mechanics become important. We try to study these naturally driven flows, and we want to predict the concentration or pollution or dilution, etc. And there we need to apply the concepts of environmental fluid mechanics. Okay. So, how EFM is different from other related disciplines? So, as we have talked about it, environmental fluid mechanics is mostly a flow related to air or water in the environment, and mostly because of the gradients like temperature or concentration, right? But if we compare this with fluid mechanics, just the basic fluid mechanics we try to see in two different ways. So first is the fundamental fluid mechanics, where we try to study the governing equations, we try to derive governing equations, right? For instance, Navier-Stokes equation or Bernoulli equation or continuity equation. These all we study in case of fluid mechanics. That is the first part of fluid mechanics, and then the next part is its application towards the engineering fields. So fluid mechanics traditionally is more about the engineering fields. For instance, this example that is given here, airfoil, right? So if you want to find how much force the airflow is generating on airfoil, we need to study the fluid flows, we need to find the pressure profile at different locations, and that will give us the force that is getting generated, or that is being applied on airfoil. And this airfoil is obviously an engineering application, because that is attached to a plane, and that is how it creates a drag or lift force for a plane to fly. Likewise, if you have a pipeline, there is fluid flowing through it, so that comes under fluid mechanics as well, right? Because there we try to calculate how much head loss is there in a pipe flow. So these are all different examples of fluid mechanics, where we try to uh, first see the fundamental derivations, and then we try to apply them in the context of engineering applications. And that's why fluid mechanics traditionally is considered to be focusing more on design and operation, right? How to improve uh, 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 the some particular machine or its performance, etc. Right? And now there is another field that's called geophysical fluid dynamics, which is similar to environmental fluid mechanics, but it is different than EFM. In geophysical fluid dynamics is particularly related to the fluid mechanics that's happening, or fluid flow that is happening because of Earth's rotation. Okay, so at geophysical fluid dynamics, we try to see the fluid flow at the Earth scale, particularly in the context of Earth rotation, right? And that's where this oceanic uh, circulation that we see from one ocean to the other ocean, that has two components. One is because of the rotation, another one is because of the temperature gradient. So the particularly the one because of the rotation belongs to geophysical fluid dynamics, and now it's very difficult to completely separate GFD from EFM, but this is usually is what considered. GFD is something that we are trying to study at the Earth scale, where we try to focus on the uh, Earth rotation, etc. And this is where we try to study things like a storm or tsunami and all those things, right? And that is why this field is related to prediction and warnings. Now the third field with which we are comparing EFM is hydraulics. So hydraulics is again related to fluid mechanics, but it is applied more towards the open channel flows. For instance, river, canal, dam, etc. And here again, similar to fluid mechanics, It is design and operation, where in fluid mechanics as well, we mostly focus on design and operation, right? So here, when we talk about hydraulics, we try to design a dam for given discharge through a river, and we try to design canal depending on how much discharge we want, how much water supply we want, etc. Right? And then there is a field called hydrology. Hydrology is related to uh, uh, groundwater or rainwater, watershed, etc. And here again, similar to environmental fluid mechanics, we have prediction and design, which is what we study in case of environmental fluid mechanics as well. So in hydrology, we focus mostly on rainwater, groundwater, and all those things. So the area is very specialized. Whereas in case of environmental fluid mechanics, we are not focusing on that particular area, but we are focusing in general on naturally driven flows. And here as well, we are trying to see the prediction and design, just like hydrology. So let's talk about prediction and design. uh, Sorry, not design, prediction and decision making, right? So we are mostly focusing on prediction and decision making in case of environmental fluid mechanics as well as in hydrology. So let's see what exactly we mean by this. So let's take these two examples again, where the second one is something we have discussed briefly, and there is this first one as well. So in first one, we are talking about groundwater contamination, right? And here we are talking about smoke release, right? So in case one, we have this waste leakage, right? So it leaks into groundwater and mixes here. It comes down, mixes with groundwater, and it contaminates the groundwater, right? Now, when we are trying to predict the amount of contamination and we are trying to make some decision based on this contamination, what we have to do is we need to find the amount of mixing, and based on that, at this location we want to know what is the concentration, right? Or what is the temperature, etc. So if C naught, if the temperature here, or sorry, concentration here is C naught, initial concentration of the contaminants that is leaking into groundwater, there will be mixing happening with groundwater, and because of that there is dilution happening, right? And once dilution happens, the concentration here, that is this concentration at this location, will be smaller than C naught. But how small compared to C naught? So now we are interested in this particular thing because we are trying to get a well here, right? And if we have a well, let's say that is an extraction well, we are trying to extract groundwater from using that extraction well. So we need to know how much will be the groundwater contaminated at that particular location. And that is where decision making comes into picture. So we want to know what should be the depth of the well, or how far it should be from the source of leakage, so that we can actually calculate the amount of contamination and whether that contamination is safe for our household usage or not, whether it is safe for our drinking or it is safe for use in our households. So this process, the predicting the mixing, and then designing your well based on how far is the source of contaminants, how much mixing is happening, what is the concentration, and what should be the depth of your well. These all come under uh, prediction and decision making, right? So this is related to groundwater pollution. Now, so this particular thing you can call It's coming under water pollution, right? Here we can call it air pollution. In this case, you have hot air coming out, as we have seen, and then because of uh, the buoyancy is rising up, but at the same time, there is mixing happening with air, and that is decreasing the concentration and temperature of the hot air, and this is actually flowing, getting mixed into the atmosphere, right? And now because it's getting mixed, it gets diluted, it concentration decreases, but from this location to a certain distance, we want to know what will be its concentration. So we are trying to find out the level of contamination, right, or level of air pollution based on the mixing. So what all it depends on. So we are basically trying to do prediction and decision making, but to be able to make a decision, right, we need to know the final concentration at a particular location. So that depends on several processes here. So to look at it very quickly, there is this convection happening, right? And then there is mixing between the gas and air, right? And then there is flow happening which is turbulent in nature, right? And then there might be the air that you have outside here might have different densities. So let's say row 1, row 2, row 3, row 4, row 5, row 6, etc. So row that you have might be a function of density, might be a function of different elevation. So this is called stratification, which we are going to see in more detail. So you see there are different processes here. One is the convection that is happening because of this hot air that is coming out from the uh, smoke smokestack, and then there is convection that is sorry, there is mixing happening between this hot air and hot gas and air. Then there is this turbulence in the system because maybe the velocity is quite high or viscosity is very small of air, right? And then there is a stratification, there might be stratification in the atmosphere, especially if you go from level 0 at the ground to maybe several kilometers, the density decreases, right, as we go up. So there is a stratification, that is called stratification, when density is changing vertically. So this is another thing that we have to see. So there are different processes that actually defines the amount of mixing, etc., right? So these are different things that we are going to see in this course. So we'll start with mixing, then buoyancy and convection, turbulence and stratification. We will also see waves, gravity currents, etc., right? Then there is vorticity dynamics. So these are different processes, and I have not listed all of them. Obviously, we are going to see more of them, but these are some of the processes that we are going to study one by one. And so we will take examples of each process, and we will try to study a particular problem in the context of that process. So we will see how these processes actually influence the uh, naturally driven flows. How do they influence the mixing or dilution of contaminants, and how we can make some how we can predict the behavior and how we can come up with some conclusion based on these processes, right? So in the next lecture we are going to see different processes in dimensionless numbers. Thank you.